Hey guys, welcome back to another video. Today we are doing graphs of sine, cosine, and tangent. Alright, so we need to quickly review the unit circle, which I've done in a previous video, just by discussing that the coordinates of the unit circle can be expressed as cos theta and sine theta as theta is measured from your positive x-axis in an anti-clockwise fashion. Okay, so what we want to point out is that the cos function is your x values as you travel around, so going left to right, and your sine values is increasing up and down, your y values. And we also have our tan function, which we've discussed before, where sine of tan of theta is sine theta on cos theta. Alright, so let's talk about graphing some of this. With our sine function, okay, we're trying to graph this. We're going to do this with a table of values. So I've done this between the values of 0 and 4, and this is what this tells me over here. This part is called the domain. The domain is an expression of the x values for which your function is drawn or existing or whatever. We'll talk a little bit more about domain in another video, but for now this is just where we're going to be drawing between 0 and 4 pi. And so I want a table of values between here, and I'm just going to go by pi on 2 as I go up. Okay, so I'm thinking about my y value in my unit circle as I travel around the circle at each of these. So 0, pi on 2, pi, 3 pi on 2, and then back to here, and then keep going. Okay, so at 0, sine of 0, angle is 0, what is my y value? Okay, this is still 0. At pi on 2, my y value has increased to the top of my circle to positive 1. As it comes down to a half a circle, then it's back down to 0. Keep going further around the circle. Now it's at the bottom at 3 pi on 2 radians. Okay, at the bottom of the circle, now it's at negative 1, my y value, it's down. And 2 pi comes back around to finish at 0. And then we keep going around as that angle increases. Okay, in effect, it's just going to repeat itself. Alright, we've got 0. Sorry, try that again. We've got 1, and then back to 0, and then negative 1, and then back to 0. Okay, so let's plot this on a graph. Let me just fix something here. Should be clear. So we've got 1 in here. Alright. So I've got a set of axes here, and I'm going to plot the points. It's going to start out at 0, and it's going to go up to 1, and then back down to 0, and then to negative 1, 0, and then start repeating. 1, 0, negative 1, 0. And we want to try and do a smooth curve as we sketch this. Mine's not going to be perfect, but I'll show you better versions of it in a second. We just want to get an idea of what this looks like. We don't want to curve or do straight lines between these points, okay? Because our y values is increasing, okay, quite quickly to begin with and then slowing down. So it looks more like a curve like this, and I'll get the hang of it in a moment. It's a pretty good attempt. It's not perfect, but we are sketching, so it doesn't need to be perfect. Okay, at pi on 2, my y value is 1. What am I doing? I'm mixing up my zeros and ones. Well, at pi, my y value is 0. That's a bit better. 0, 0, pi on 2, 1, so on and so forth. Okay, we want to pay attention to these intercepts and the peaks and troughs of my function here. And you'll notice that after 2 pi, once we've gone around the circle once, then it has just repeated itself. Okay, this repeating nature gives us what we call periodic functions. Let's look at cos. I've done this for a smaller sequence of values here, and I'll just sketch my unit circle on the side. Now, cos are my x values as I go around, kind of from left to right along here. At 0 degrees, or 0 radians, then my x value is at 1. Okay, 1, 0, better. 1, and then as it increases to 90, we are on the y-axis, which means 0 in the x direction. That's to -1 as it comes back down to this side of my circle. And we're all the way over here, back to 0, and then up to 1 again. And it will repeat this again. So let's plot my points. And then start repeating. And run that a little bit, but see how that goes. Again, slow change. And not straight lines. Again, not perfect, but you will notice at that point you get the same values again, and it would go again and again and again and again. Infinity times, really. So let's have a look at what our tan function is. Now tan's a little bit trickier to describe, okay? So I'm going to do this more electronically, but I'll do a sketch afterwards to show you how that's done. But our tan function, as an aside, is essentially the length between this extension of the hypotenuse of this angle here and where it meets this tangent. So this line on the outside of my circle is the tangent to this circle, and the length here, that distance AT, is tan of theta. Now we can think about this as these triangles OBC, and triangles OTA are similar. And if you remember your similar triangles, which you might not, you can do the ratio between their sides are equal, and so y over x is the same as the length of AT to the radius of the circle, and then this is also your tan function. We discarded y on x previously. Let's move on. All right. So tan function. Actually, I'll go to this idea here. All right. As my angle increases, the length of this tangent increases slowly, or actually quite quickly. And once it hits 90 degrees, this is an important part, it is vertically upwards. This is what we call an asymptote. It's undefined at 90 degrees, which you might remember from your exact values before, and then it continues around starting from the negative side and appears all the way down to the bottom of the graph down here, and keeps going around 180, we're back to 0, and then it starts to repeat itself up 270, back to 0, to undefined, and then 360, come back to 0. So the sketch isn't going to look perfect, but starting from 0, slow increase, then it heads in that direction. Doesn't quite I think I spelled that right. I've been spelling it wrong for years. I just found out last year. But this is asymptote. Yeah. Anyways, that means it never touches that line, and then it comes back quite quickly. And this is a terrible sketch. Okay, and it keeps repeating. So on and so forth. Alright, let's go back to the much better diagram that we've got here. That's what it looks like here. Alright, and you might appreciate this little diagram that we've got of the cos and sine, cosine and sine functions. As it travels around the circle, your x value is changing, creating your cos function, and the y value is changing, creating your sine function. And so you'll see it repeat again and again and again and again as it goes around that circle. Alright, so we have our sine function. Best looks like that. We have our cos function, which is a very similar curve, but it's actually slightly out of place to the sine function. Talk about that another time. And the tan function, okay, which has asymptotes at 90 degrees, 270 degrees, or pi on 2 radians, 3 pi on 2 radians, so on and so forth. And you'll see these quite a bit. So this website, by the way, is called Desmos. It's a very useful thing that we have here. Very good at graphing. Okay, so there's your asymptote there. So those are our three functions. Now we just need to finish up with a quick description of some of the other things that you might be or might have to discuss. We talk about the amplitude, which is the difference between this midline of my function, which is usually symmetrical around, unless it's tangent, and then it's slightly different, but that actually doesn't have an amplitude because it's undefined. Anyways, the amplitude difference between your height and the midline, the period is the length before it starts repeating itself. Now you don't want to say that it starts repeating itself in pi, okay, because it actually doesn't. It starts to decrease downwards. So what we've discussed is that the amplitude for sine and cosine from our, here's your cosine function, the amplitude is a total of 1. Again, it's how tall from the midline your function is, and it starts to repeat itself, as we mentioned, throughout the example every 2 pi, a complete revolution of that circle. Tan's a little bit different because it has no amplitude because it's undefined height, and its period is actually pi rather than 2 pi. Okay, lastly we have vertical translations and negative functions here. Okay. Vertical translations means we can move this function up and down. Okay. Looks a little bit like this. So I've got the sine function drawn at no vertical translation. That's what we're used to seeing at the moment. +1, so it's actually gone, moved that function up by 1 unit for all of its values. Or I've got -3 down there, so it's decreased, going from 0 to -3 here. There's a difference of 3 between all of these values. 1, -2. Okay? So that's what your vertical translation does, that constant at the end of your function, after your function, moves it up and down. Okay? And we have the negative function. So let's look at cos and negative cos of x. And you'll see that it's actually a reflection in that x-axis. Everything that was positive has now become negative, and everything that was negative has now become positive. It flips it around the x-axis, and the same thing happens with sine. Okay, there's sine, and there's negative sine. So it started at 0, but then started to go negative down here first, rather than the positive that we saw in the positive sine function. Same thing happens with tan. Okay, a little bit trickier to see. Okay, but there is positive tan, and there is negative tan. Alright, well that's all I have for today, but as a closing problem, I'd like us to think about and sketch this function here. Sketch y is equal to negative sine of x plus 1. Okay, so sine x is separate, then you're adding 1. And for the domain between negative pi and pi, so with your sketch, you're going between negative pi and pi. And what does your function look like? This one here. You can use software, you can use Desmos, you can use calculators, do tables of values, whatever you'd like. Give it a shot. Let me know how it goes.